So thanks to Pallavi and the other organizers for this invitation. It's great to see so many people interested in this topic. Yeah, so as she already mentioned in her earlier talk, there will be a couple of lectures on popular matchings. So let's start. Now this is Pallavi. This is scrolling up. I think we should shrink the screen maybe. हर स्क्रीन दो बार आ रहा है. ठीक
PDF ही ऐसे बना हुआ है.
अच्छा अच्छा. Have a bipartite graph where every vertex has a strict ranking of its neighbors, and as we all know, this is a very well studied model with many real world applications such as matching students to schools, residents to hospitals, agents to jobs. And as you all have been seeing, I'm sure in several talks, what one seeks here is a stable matching. A stable matching is considered an optimal matching in this setting. So just for the sake of completeness, I had this definition of stable matchings. All of you are very familiar with it. So the red matching is stable, the blue one is not, because the edge between the two middle vertices blocks the matching. So is everything okay so far? And as we all know, stable matchings always exist. That's a famous result of Gale and Shapley from more than 60 years ago. And we can find one efficiently. So again, for the sake of completeness, I just thought, let's just run Gale-Shapley algorithm on a toy instance. So we have two, let's call them agents, two jobs. Both these agents have the same top job, that's B. And when we run Gale-Shapley algorithm on this instance, where agents propose and jobs dispose, well, both these agents prefer B to, in fact, this agent is not even adjacent to T, so both of them prefer to B, both of them propose to B, and since B prefers S to A, the job rejects A's proposal and accepts S proposal, and there is no other proposal to make because A has no other neighbor, so we get this single edge matching. So that's the Gale-Shapley algorithm on this small instance. And stable matchings have been used in so many real world applications, in particular in matching students to schools. So this is an article from New York Times from 2014. It's been used to match students to colleges in France and here in India too, to match students to engineering colleges. And in fact, the oldest application of stable matchings was to match medical residents to hospitals. And in all these applications, we want a large matching. We want to match as many students as possible to schools and colleges. We want to match as many, in fact, we want to match all residents to hospitals. And in all applications, we want a large matching. And as Pallavi has already said, the rural hospitals theorem tells us that even though there are an exponential number of stable matchings, all of them have the same size. And in particular, the set of vertices matched in each of these matchings is the same. So that is a bit of a dampener. And as we saw in this toy example, the size of a stable matching could be only half the size of a maximum cardinality matching. So if we went for the maximum cardinality matching, both these residents, let's call them residents or agents, could have been matched, but now insisting on stability is in fact saying this agent or resident has to be left unmatched, which really speaking is not a very nice property and not desirable. So stability is too strong a notion forbidding blocking edges is constraining the size of the resulting matching. So if we went for a maximum cardinality matching, we would have been better off in some sense in having both the residents or agents employed, and now we are constrained. So let's call these drawbacks of stability. We are compromising on the size by insisting that blocking edges are forbidden. And also we are empowering every edge with the power to block a matching. Maybe this is too strong a notion. So can we relax stability so as to deal with these issues? So what is it that we desire? We want to say, let's have a larger set of feasible matchings so that all stable matchings for sure are there in the set, and we also have larger cardinality matchings in the set. Rather than empower every edge with this veto power to block a matching, so rather than give the power to say this is a bad matching, let's in fact give such a veto power to the entire set of agents or the entire set of vertices. So as we saw in this example, this particular edge had the power to block the maximum cardinality matching. So let's not give any edge such a power. Let's shift the focus from such veto power to some kind of collective decision making, something that is good for the entire vertex set. And this is the notion of popularity at a high level. I am being very abstract here, we will concretize it soon. So this is based on the idea that any two matchings can be compared by holding a head-to-head election between the two matchings. And who are the voters in this election? Every vertex casts a vote for whichever of these two matchings it prefers. So when do we say a vertex prefers matching M to matching N? If the partner it gets in M is better than the partner it gets in N, it says I prefer M to N, and if it gets the same partner in both, it abstains from voting, and being left unmatched is the worst possible state. So let's see an example. So we have 6 vertices here, and let's hold a head-to-head election between the red matching and the blue matching. So who votes for whom? Let's look at the top 2 vertices. Whom does this vertex vote for? Does it like the red matching better or the blue matching better? Yeah, exactly. So it abstains from voting. It says both the matchings are the same. Similarly, this vertex. What about this vertex? Exactly. Similarly, so does this vertex. It gets a better partner in the red matching compared to the blue matching. And what about the bottom 2 vertices? Fantastic. So this election ends up with votes being cast like this. The top 2 vertices abstain, so I have left them uncolored. The middle 2 vertices prefer the red matching, so I have colored them red. And the bottom 2 vertices cast votes for the blue matching, so I have made them blue. And so when you count the votes for red versus blue, it's 2 versus 2, it's a tie. Now let's look into the picture, the green matching. And let's consider these 2 matchings. So we can go through each vertex one by one as we did. And believe me, these 4 vertices like the red matching, and the remaining 2 vertices prefer the green matching. So the red matching wins the election since it gets 4 votes. So a popular matching is one that does not lose any election. So the green matching for sure is not popular. It has lost at least one election. Whether the red matching is popular and the blue matching is popular, we still have to hold other elections to see that. And this notion of let's have elections between pairs of candidates is in fact a really old and classical notion from more than 200 years ago, and this was proposed by the Marquis of Condorcet, a French philosopher and mathematician. So I'll give a small example of what is a Condorcet winner. So let's say there is an election between 3 candidates A, B and C, and 30% of the population. Now we are not talking about matchings, I am talking about general elections. So 30% of the population, that is voting population, has this preference order. For them, A is the top choice, B is the second choice, C is the third choice. For another 30% of the population, the order is this way, and for the remaining 40%, let's say the order is this way. and let's hold head-to-head elections between each pair of candidates. So let's compare A and B. So how does the population vote? A gets 70% of the votes and B gets 30% of votes. So A wins the election. So let's use this notation to say A defeats B in their head-to-head election. Let's hold elections between A and C. Similarly, A wins the election against C. Such a candidate is called the Condorcet winner. So Condorcet winner is a very strong notion. It's not just saying let everybody cast a vote for whoever is their top choice. It says let's hold head-to-head elections between every pair of candidates, and if there exists a candidate who defeats every other candidate in this head-to-head election, such a person is called a Condorcet winner. And according to the Marquis of Condorcet, who proposed this notion, such a person is a true winner. He called it a Condorcet, maybe people later called it a Condorcet winner after him. So we are not really insisting that our candidate should defeat everyone. All we are saying is our candidate should not lose to anyone. So we call it a weak Condorcet winner. So what's a weak Condorcet winner? In the head-to-head election between our candidate X and any other candidate, this notation, which looks like greater than or equal to, means either X wins the election against Y or it's a tie. X does not lose the election. Is this okay? So not losing is this greater than or equal to symbol I am using there. Unfortunately, Condorcet winner and even weak Condorcet winner are rather demanding notions. Such a winner need not exist. So this notion of not losing to or winning, this notion is actually, it's not a transitive notion. We can have cycles like this. Let's check it on this example, where 1/3 of the population says A is better than B, better than C. Another 1/3 says B better than C, better than A. And another 1/3 says C better than A, better than B. So let's hold a head-to-head election between A and B. A wins the election because it gets 2/3 of the votes. B and C, B wins the election, and C and A, C wins the election. So we can have cycles, and there is no Condorcet winner or weak Condorcet winner here because every candidate is losing to some other candidate. Well, back in our setting of matchings, what we are talking about by saying let's hold head-to-head elections, our matching should not lose to anyone, what we wanted is a weak Condorcet winner. So we didn't want M losing to any other matching, and we in fact gave the name popular matchings to such a class of matchings. And as we saw in the example, it looks like popular candidates need not always exist. Interestingly, in the world of matchings, where every vertex, that is we have a bipartite graph, every vertex has a strict preference ranking over its neighbors, Condorcet or weak Condorcet winners rather always exist, because as Gardenfors noticed almost 50 years ago, every stable matching is popular, and as we know, stable matchings always exist. So this proof is just 2 lines. Why is every stable matching popular? So let's hold an election between a stable matching S versus any matching N. If some vertex casts its vote for the rival matching for N, then U for sure is matched in N, otherwise there is no question of preferring the other matching to S. Its partner in that rival matching has to prefer the stable matching to N. Why is it? Otherwise, if both U and its partner in N prefer each other to the respective partners in S, then the edge between U and its partner blocks S, whereas we know a stable matching has no blocking edge. Is this argument okay? So whenever you say some vertex U prefers the rival, then it's invariably the case that its partner has to prefer the stable matching. So when we count the number of votes for the rival matching and sum the number, that number is at most the number of votes that the stable matching wins. I'm sorry? Exactly, it's partner in N, because U is certainly matched in N, otherwise there is no question of preferring the rival matching. So it has a partner in N. Let's look at that partner. That partner is putting its vote for our stable matching. So the properties of popular matchings, let's look at them. We wanted to shift the focus from giving veto power to every edge to collective decision making, and by definition, let's count the total number of votes that is capturing collective decision making. So let's put a tick. Popular matchings by definition satisfy this property, and as we saw, every stable matching is popular. And in fact, rather than just say every stable matching is popular, a small argument will show that stable matchings are actually minimum size popular matchings. So popular set of popular matchings hopefully has larger matchings, and our goal is, let's find a maximum cardinality, a maximum size popular matching that hopefully has a size larger than a stable matching. So that's our goal for the rest of the talk. Is there an efficient algorithm to find a maximum size popular matching? We know a nice algorithm, the Gale-Shapley algorithm, to find a minimum size popular matching, but that's not of interest to us. We want to find matchings of size larger than stable matchings. So what's the first attempt to find a maximum size popular matching? Since we know how to compute a minimum size popular matching, that's a stable matching, let's start with a stable matching, run Gale-Shapley algorithm, find any stable matching, and let's try to mimic the maximum cardinality matching algorithm. How does the maximum cardinality matching algorithm work? Huh? Exactly. Let's try to find augmenting paths with respect to our current matching. So let's take a stable matching, and actually we do not know how to implement this step to check if the given matching is a maximum size popular matching or not, but let's just sort of ignore it for now, and let's look at a more abstract, at a high level. Let's try to mimic the approach that she suggested. Find a suitable augmenting path with respect to M. Now even suitable augmenting path is sort of ill-defined, but let's just leave it at that high level idea stage. Let's find a nice augmenting path and augment our matching along that path. Then the matching increases in size. And what is it we mean by suitable augmenting path? So we want to find an augmenting path so that once we augment our matching along the path, the resulting matching is popular. Now how to do all this, let's put it aside, but at an idea level, let's contemplate this. Is the idea okay? Let's start with a minimum size popular matching, that's a stable matching, and look for a nice augmenting path, augment, and now again repeat the same step. Unfortunately, this idea doesn't work. So this is a small example here. On 8 vertices, there are two stable matchings here. This pair of horizontal edges, this pair of vertical edges. The two kind of green matchings are stable here, and there is in fact a perfect matching, and that's a maximum size popular matching. That's a popular matching, and because it's perfect, it is a maximum size popular matching. So there is a stable matching of size 2, and hence there is a popular matching of size 2, and there is a popular matching of size 4, but there is none of size 3. So any of the size 3 matchings that you consider here, that is a pair of red edges and one green edge, or the other way around, we can check none of them is popular. So this kind of an augmenting path type approach wouldn't work, because you start with a size 2 matching, then you realize in fact none of the augmenting paths seems to give us a popular matching. We might think in fact this is a maximum size popular matching, but that's not. So in fact the Gale and Shapley algorithm is such a clean and elegant algorithm. Can we take inspiration from that? Can we somehow adapt the Gale-Shapley algorithm itself to find a maximum size popular matching? But stability and popularity seem, very different in nature. So stability is such an easy to check concept. You just have to go edge by edge and check none of them is a blocking edge. Whereas popularity, we're talking about, all possible matchings. The set of all matchings is exponential size, and it requires comparing this matching with all matchings. So for any popular matching, is there a simple way of checking that it's popular or not? Just as there was a simple way of checking if a given matching is stable or not. Does popularity also carry such a simple certificate of its popularity? Moreover, since we want to find a maximum size popular matching, we also need to check, given a matching, is it really the case that no larger matching is popular? So we really have to answer these questions. So let's go back to our toy example, the one on which we ran Gale-Shapley algorithm. So in this example, the perfect matching, the one of size 2, is indeed popular. So that's a maximum size popular matching here. Whereas as we saw when we run Gale-Shapley algorithm on this instance, what we get is a middle edge. So if we want to adapt Gale-Shapley algorithm to find a maximum size popular matching, we can't just run it on this graph. It will give it the middle edge as the output. So can we somehow come up with a new instance? That is, can we tweak this instance into some other instance, G prime let's call it, so that the perfect matching is the stable matching in this new instance G prime. So let's consider this idea. Suppose we replace every edge in the given graph by a pair of edges, one red, one blue. So we replace every edge by two parallel edges as shown in this figure. Is this okay? This was originally this Z graph. I replaced every edge by two edges, one red, one blue. So let's say every agent, every vertex on the left side prefers a red edge, any red edge to any blue edge, and symmetrically every vertex on the right side prefers any blue edge to any red edge. So in fact, coming up with the numbers, the graph G prime, where we have replaced every black edge by this pair of red and blue edges, the preferences are as follows. So let's focus on S. S original preference, rather than say B is its top choice, T is the second choice, let's say this edge SB is its top choice originally and this edge ST was the second choice. Let's put preferences on edges rather than on vertices. So original preference order of S was SB is better than ST. How is it in this new graph? Are you all fine with this, what I wrote? Any red edge is better than any blue edge. Within red edges, it is the original preference order. Within blue edges, it is the original preference order. So S says this red edge to B, that's my top choice. The red edge to T is my second choice. The blue edge to B is my third choice. Blue edge to T is my fourth choice. A had only one neighbor, so the red one is better than the blue neighbor. Let's go to the other side now. The preference order for B to begin with was SB is the top choice and AB was the second choice. And vertices on the right say blue is better than red, so its choice in this graph G prime becomes, its preference order becomes as follows. Blue edge SB is top choice, blue edge AB is second choice, red edge SB is third choice and red edge AB is the fourth choice. Is this okay? So this is really crucial. So recall the original graph had only the middle edge, it had only one stable matching, that was the single edge SB. Interestingly, in this red blue graph, neither the red edge SB nor the blue edge SB is stable. Can you tell me why? Why is the red edge SB not stable? What's the blocking edge here to the red edge SB? Huh? Yeah, the blue edge AB blocks it because B prefers, it has rank 2 versus rank 3. B prefers the blue edge AB to the red edge SB and A prefers to be matched along any edge compared to be left unmatched. Similarly, when you look at the blue edge SB, S goes through such a thing, it would rather be matched along the red edge ST compared to the blue edge SB. So neither the red edge SB nor the blue edge SB is stable in this graph G prime. So what is the stable matching here? So let's actually, some people have already checked it, but let's run it. So back to our original algorithm, A and S propose to be, that is along the red edges, that's their top choice edge. So B receives 2 proposals, it rejects A's proposal and tentatively accepts S proposal. I am saying tentatively because if it gets a better proposal, it's going to reject this also. Then A has to go to its second choice edge, which is the blue edge AB, it proposes. Now B has a better proposal, so it rejects the red proposal from S and tentatively accepts A's proposal along the blue edge. Now S has to go to its second choice, that's the red edge, and T has received a proposal. It's the first proposal it receives, so it happily accepts it for now. And actually there is no one else left to propose. Both the agents have been accepted, so that's the end of the algorithm. So indeed, as someone said, the tentative proposals are now definite and we get the matching that we wanted. So we wanted this perfect matching, we got it. Just ignore the colors now and we have the matching that we wanted. So this was such a small example, does it generalize? And our typical experience tells us, these things work in such small examples, they don't generalize. To our delight, it generalizes. So let's look at this algorithm. Given any bipartite graph where vertices have strict preferences over their neighbors, let's construct the red-blue graph. Run Gale-Shapley algorithm in this red-blue graph. You will get a stable matching. Ignore the colors. So the difference between M prime and M is, this is a colorful matching, you have just ignored the colors. And the claim is, this always works. So it's just Gale-Shapley algorithm, but not in the original graph, in this red-blue graph. How do we prove it? I've just made a claim. So it is indeed the case that every popular matching has a nice and compact certificate of its popularity. So we do not really need to go around checking this matching against all the exponentially many matchings in the given instance. This certificate is somehow encoded in these red-blue colors. So these red-blue colors do have a meaning. So though we just said ignore the colors, well, we are going to go back to the colors to define this certificate of popularity. So to define the certificate of popularity, we need to go into linear programs. So let's first translate this whole notion of popularity into some kind of an edge weight function. So we have a particular matching M with us, that's a matching returned by that algorithm we saw in the previous slide. Let's define an edge weight function that depends on this matching M. So what is the weight of any edge AB? It is the sum of the votes of the endpoints of the edge for each other versus their respective assignments in M. So what do we mean by sum of votes? What is the vote of a vertex? For any vertex V, its vote versus two neighbors u and u prime is, if it prefers u to u prime, it gives a vote of 1. If it prefers u prime to u, it gives a vote of -1. And if u equal to u prime, that's what otherwise means, it gives a vote of 0. It is indifferent. So let's define such a vote function and say the weight of an edge is the sum of the votes of the endpoints of the edge for each other. So the weight of every edge is a value in the set 0, +2, -2. Do you agree with this? Why can't it be +1 or -1?
Sure.
Exactly. So either both are +1, both are -1, one is +1, one is -1. You can't have a 1 and a 0 because the only way to have a 0 is A equal to M of B. A is B's partner, in which case B is also A's partner, and so you would have 0 + 0. And an edge has weight 2 if and only if it's a blocking edge to M. So weight 2 is just another way of saying the edge blocks M. So it would be more convenient to deal with perfect matchings. So let's just put self loops at all vertices, and rather than say a vertex is left unmatched, we say it is matched to itself along the self loop. So we need to extend the edge weight function to also define it on self loops, and it's just the vote of a vertex for itself versus its assignment in U. So versus its assignment in M, I'm sorry. So if M is matching U to itself, the weight on the self loop is 0. Otherwise, M is matching you to a non-trivial neighbor, and so to be matched to itself is a negative vote, it's minus 1. So we just extend the edge weight function to take care of self loops also. And this whole, even if you didn't really understand all the fine points of the edge weight function, just remember this. We have defined this weight function so that for any perfect matching n, the weight of n under this edge weight function is just the difference between the number of votes that n gets and m gets in their head-to-head election. So the whole head-to-head election between two matchings, whether m wins or n wins, is just being captured by this edge weight function. So we have fixed one matching m here, and to know the results of all elections involving m as one candidate, it's in a way the same as asking for, under this edge weight function, is it the case that any perfect matching has weight at most 0 or not? If there is even one perfect matching with weight positive, it means that matching wins this election against M.
We already defined weight for age.
Yes.
Now we define weight of age.
Yes.
So
Sorry. Yeah, weight of a matching. Weight of the matching is just sum of weights of edges in the matching. Sorry. I did not clearly define it. I just mean let's add up the weights of all edges in a matching. Because a matching is just a set of edges. For each edge we define the weight, add up all the weights. Sorry. So weight of n, shall I just write it on the board or is it okay? So weight of the matching n is summation weight m of every edge in n. And the way we have defined the weight function, it easily follows, if you should just write down the steps, that the weight of a matching is the same as, let's count the number of votes that n wins, the number of votes that m wins, and take the difference between the two. So if m is popular, that means nobody gets more votes than m. So this edge weight function, for every perfect matching, it's the case that its weight under this function is less than or equal to 0. So in other words, every perfect matching, when edge weights are given by this function, has weight at most 0. So let's write the linear program for max weight perfect matching. It's a very simple LP. I hope you are familiar with this. So we have augmented, so delta u is the set of edges incident to vertex u. We have also augmented its self loop, so I have written it separately. So every vertex is matched. It's either matched by the original m to someone, and if it's not matched by the original m, we just augmented m with self loops. So for sure every vertex is matched. Yeah, and so this looks like it's a fractional LP, but this is finally all its extreme points are integral. So when we solve the LP, we'll always get, there is a 0-1 solution. So this LP is the max weight perfect matching LP. So M is popular if and only if the optimal value of this linear program is at most 0. That's what we said in the previous slide. We have written down explicitly the linear program for max weight perfect matching here. Please stop me if something is unclear. Yeah, so let's look at the dual LP. So are all of you comfortable with writing the dual LP? So we need to introduce dual variables, one for every constraint here. Let's not bother about the non-negativity constraint. So the dual variables are one for each of these equalities. Alpha sub u is a dual variable corresponding to the constraint that every vertex has to be matched. And the constraints in the dual LP are, in a way this translates to every edge has to be covered. You have to come up with an alpha value for every vertex so that the sum of the alpha values of the endpoints of every edge is at least the weight of the edge, and each alpha u has to be at least the weight of the self loop at u. That's what you just syntactically write the dual, you will get these constraints. And LP duality tells us that M is popular if and only if the optimal value of the dual LP is at most 0. So, for us to show the matching returned by our red blue by running that Gale-Shapley algorithm on our red blue graph is popular, if we can come up with a dual feasible solution whose objective function value is at most 0, then the job is done. So, there is another proof that every stable matching is popular. So, every stable matching has a very simple dual certificate. So, a dual feasible solution whose objective function value is 0 will be called a dual certificate for that matching. Every stable matching has a simple dual certificate. Take all alpha u values to be 0. Why is that dual feasible? It's because a stable matching has no blocking edge. So, there is no edge with weight 2 in a stable matching. So, every edge has weight either 0 or minus 2. Take every alpha u to be equal to 0, then every edge is covered. So, is this argument okay? So, this is one proof that every stable, a different proof from what we saw, that every stable matching is popular. So, if you write this dual LP for any stable matching and take each alpha to be 0, in fact all the constraints are satisfied because every edge weight is either 0 or minus 2. So, 0 plus 0 is greater than 0 or minus 2 is perfectly fine, and every self loop has weight 0 or minus 1. So, 0 greater than or equal to 0, 0 at least minus 1, both are satisfied, and sum of all these 0 values is 0. So, every stable matching will satisfy this property that the optimal value of the dual LP is at most 0, because we constructed a dual feasible solution whose objective function value was exactly 0 and is a minimization LP. So, the optimal value is at most 0, hence every stable matching is popular. But our problem was really to prove the matching output by our algorithm, the red blue graph. That's popular. Does that matching admit an easy to describe dual certificate? Because that may have blocking edges. In fact, the perfect matching in our toy example had a blocking edge. The middle edge was blocking that matching. So, we can't say take alpha u to be 0 for every u. That's certainly not dual feasible. As we said, its certificate was somehow being captured by these red blue colors. So, for every agent A, let's define its alpha value as possible. If it is matched along a red edge, set its alpha value to be plus 1. If it's matched along a blue edge, set its alpha value to minus 1. And if it's left unmatched, so we're talking about M prime, which is the stable matching in the red blue graph. So, in the red blue graph, either a vertex is matched along a red edge or a blue edge, or is left unmatched. Accordingly, set the alpha values as given here. For every vertex on the right hand side, what we call jobs. So, if it's matched along a red edge, give it minus 1. If it's matched along a blue edge, give it plus 1 alpha value, and if it's left unmatched, set it to 0. So, this is a useful picture to keep in mind. So, let's partition the vertices as the agents matched along red edges, we will put them in A0. The jobs matched along red edges, we put them in B0. The agents matched along blue edges, let's put them in A1, and the jobs matched along blue edges, let's put them in B1. The agents left unmatched and the jobs left unmatched, we put them in A1 and B0 respectively. So, it's just a useful picture for us, and we assign the alpha values as follows. Alpha value is plus 1 for these vertices and plus 1 for these vertices. It's minus 1 for the vertices in the, what should I say, northwest and southeast. So, northwest and southeast vertices are minus 1 for matched vertices. For unmatched ones, they are 0. And for the southwest and northeast vertices, alpha values are always plus 1. They are always matched and it's plus 1. So, we need to show this assignment of alpha values is a feasible solution to the dual LP. And we will also show the sum of all the alpha values. This is the objective function value, that's 0. So, this will mean the dual optimal solution is at most 0, and that will prove M is a popular matching. Is this okay? This is outline of our proof of popularity, that a proof that M is indeed a popular matching. So, why is this assignment of +1, +1, -1, -1, 0, 0, why is it dual feasible? First, let us show the easier constraint, that alpha u is at least weight along the self loop. So, for a matched vertex, alpha u is either +1 or -1. So, it is always at least -1, and the weight of the self loop for a matched vertex is -1. And for an unmatched vertex, we have alpha value to be 0, and for an unmatched vertex, weight of the self loop is exactly 0. So, this constraint holds for all vertices. And the more non-trivial proof is to show this constraint, that is every edge is covered by the sum of alpha values of its endpoints. We will use the stability of M prime in the instance G prime, because that is all we know, that M prime is a stable matching in the red blue graph G prime. And so, once we show the lemma, job done, alpha is dual feasible. So, let us just take that for granted for now, and let us prove sum of alpha values is 0. That is actually easy to see. So, every edge in M prime is either a red edge or a blue edge. So, either the endpoints, one endpoint has, it is always the case that one endpoint has alpha value +1, the other endpoint has alpha value -1. So, alpha A plus alpha B is always 0, and for unmatched vertices alpha value is 0. So, sum of all the alpha values is 0. So, M is a popular matching once we prove our lemma. So, let us prove our lemma. So, it is just dealing with a few cases. So, what happens when the alpha values of both endpoints are -1? So, that means A is sitting in A1, B is sitting in B0, and A is matched along some blue edge and B is matched along a red edge. So, we claim A prefers C to B and B prefers D to A. So, both A and B prefer their respective partners in M to each other. Why is it? So, we claim A never proposed along the blue edge AB. How do you justify this? Exactly. So, if A had proposed along the blue edge AB, since any vertex, any job, any vertex in the set B prefers a blue edge to a red edge, B would have happily accepted any blue offer to any red offer. So, B would not be matched along the red edge BD. So, the fact that B is matched along a red edge means it never received any blue offer. In particular, A never proposed along the blue edge. And furthermore, we also claim B rejected A's proposal along the red edge AB. How do we justify that? So, A prefers red edges to blue edges. So, A got rejected along every red edge to all its neighbors. In particular, B rejected A's proposal along AB, because if B accepted A's proposal along the red edge AB, A would never have gone even lower to propose along a blue edge. It is just a question of how we define that vertices in the set capital A prefer red edges to blue edges, and vertices on the right prefer blue edges to red edges. So this means both alpha A and alpha B, though they are -1 each, so they sum up to -2. It is also the case that the weight of the edge AB is -2. So, the sum of votes of A and B for each other versus their respective partners is indeed minus 2. B prefers D to A, so it has a vote of minus 1. A prefers C to B, it has a vote of minus 1. So the weight of the edge AB is minus 2. So everything is perfect. So let's look at the case when both the alpha values are plus 1. There is nothing to prove here because by definition the weight of an edge is 0, plus 2 or minus 2. So 2 is at most the weight of an edge always, and we are saying each of the alphas is 1. So this constraint obviously holds. So let's look at the case when one of the alpha values is plus 1 and one is minus 1. Say alpha A is plus 1, alpha B is minus 1. This means both the red edges are in M prime, and because M prime is stable in G prime, the red edge AB does not block M prime. So either A prefers C to B or B prefers D to A. So the weight of the edge is at most 0, hence this constraint also holds. Symmetrically for the other constraint, when alpha A is minus 1, alpha B is plus 1. Yeah, so let's just spend a few seconds on this case. Suppose one of the endpoints, that is, let's say alpha A is 0. Then because M prime is stable in G prime, the blue edge AB does not block M prime, which means A has already proposed along the blue edge AB, and B still did not find this blue edge interesting enough. So for sure it is matched along a blue edge, and moreover it is matched along a blue edge to a neighbor that it prefers to A. So alpha B is plus 1, B is in the, what did we call it, the northeast part of our vertex partition, and the sum of alpha values is 1, and the weight of the edge is 0 because A prefers to be matched to B, then be left unmatched, but B prefers its partner to A, so it has a vote of minus 1 along the edge. So an analogous analysis holds when alpha B is 0. So all cases have been dealt with. So this setting of alpha values is indeed dual feasible, and this proves M is popular. We still have another thing to prove, that M is a maximum size popular matching. But the proof is right here actually, the proof that M is a maximum size popular matching. Can someone tell me? So M is a popular matching is done, but we are not happy with just finding any popular matching. Our goal was to find a maximum size popular matching. How do we show no larger matching is popular? Any ideas? So I think I'm already exceeding my time perhaps, so let's go to the proof. So let's look at any edge incident to an unmatched vertex A. So recall that alpha A is 0 while the other endpoint had alpha value plus 1. That was this reasoning, this analysis. I'm just going back to this analysis. So the constraint is slack. The left hand side is plus 1, the right hand side is 0. So this is not a tight constraint, it's a slack constraint. And there is this very useful theorem from linear programming called complementary slackness. So any matching with a slack edge cannot be an optimal solution to the primal LP. So if you go back to the maximum weight perfect matching LP that we wrote, and if you look at any feasible solution that contains a slack edge, that cannot be an optimal solution to that LP. So this is complementary slackness. So what does it mean by saying it's not an optimal solution? The optimal solution has value 0, and because M itself is a feasible solution and its weight is 0 under this edge weight function. So if it's not an optimal solution, that means the weight of any matching that contains a slack edge is strictly smaller than 0. And the way we define the weight function, it is a difference in votes, in the number of votes that N wins and N wins. That means M gets strictly larger number of votes than N. So any matching larger than M is unpopular. So that's the proof M is a maximum size popular matching. So one last slide. So we said a stable matching could have size at most half the size of a maximum cardinality matching. We have in fact a better size guarantee for a maximum size popular matching, because we claim there is no length 3 augmenting path with respect to a maximum size popular matching. If there is such a length 3 augmenting path, as we saw in our toy example, either the blue edge AB or the red edge ST block such a matching. So such an edge we wouldn't get such an augmenting path with respect to R matching M. So every augmenting path so that is augmenting path in this symmetric difference M XOR maximum size matching. So is this okay? I am sort of saying it too fast perhaps. So we are claiming that if you look at the symmetric difference between M and any maximum cardinality matching in G, so M max need not be popular, stable, anything, it is just a maximum cardinality matching. But the symmetric difference between M and M max cannot have a length 3 augmenting path, because that would contradict the stability of M prime. M prime is the stable matching in the red blue graph, which gave us this matching M. So any augmenting path in the symmetric difference has length at least 5, means the cardinality of M is at least 2/3 the cardinality of a maximum cardinality matching in G. So this is better than a stable matching where we could have a half instead of 2/3. Yeah, that's all I have to say. Thanks.
Thank you, ma'am. So we will now have a 20 minutes coffee break, and then we will meet at